the next topic I was going to cover is noise power ratio simulation. For those of you who don't know it, let me just briefly explain it here. You have an amplifier and you input this is the spectrum of the input signal. You input this into the amplifier. Okay, this is frequency. And the output is the same, except due to nonlinearities in the amplifier, this notch in the middle gets filled up due to effectively intermodulation distortion. So anyway, this is called noise power ratio, and it's a ratio of the power in the notch to the power in some band that's the same that's out of the notch. So you can do this. This is commonly done in, say, satellite systems, satellite communication test systems. But you can do this using an envelope simulation or using harmonic balance. There are two ways of doing it, and I can go over both of them. Let's see. Find examples. Okay, so where are they? So let me. Okay, this is an example of an NPR signal. Okay. So basically, this is the result. This is what we're looking for. And I've zoomed in on the spectrum at the output of an amplifier. And I'm sweeping the input power of this is the output spectrum, kind of zoomed in on the notch area. And I'm applying the same test signal with this notch. And I'm calculating the power in the notch. I'm doing an average over the spectrum, and also calculating the power outside the notch. And I take the ratio, the ratio of the input signal notch is minus 80, like minus 86 roughly, and the NPR gradually gets worse. Basically, the notch fills up, and this is the output power. And then you can also calculate air vector magnitude. We haven't talked about air vector magnitude at all today, but certainly you can calculate that from a noise power ratio signal. And the test signal in this case was a WLAN 11AX 160 megahertz signal with a notch added to it. Okay, so the setup here is, this has a number of different tests in it. One of them is just a simulation of well, you have to generate the signal first. So here's, I'm generating the signal by using these two filters. This is a bandpass filter, raised cosine bandpass filter. And I also have a band stop filter. And so this allows you to investigate the shape of the test signal, and that I think it's useful to do this. You can generate an arbitrary test signal, but the output looks like this. Then we can you can actually use noise as a test signal if you want. this is a way of generating a test signal for NPR simulation. This is an ideal IQ modulator, and we have noise, a noise source for the I input, and a noise source for the Q input. And we just modulate that noise onto a carrier using the envelope simulator, and then we send that noise modulated signal through the filter and the notch, the bandpass filter and the notch, and we get this output. So we get this relatively narrow band signal, and there's a notch here. So if I zoom in on it, just like that. So you can experiment with different test signals. And then, okay, this is an example. If you wanted to use a WLAN signal, okay, so this one uses a VT dataset source. I'm sorry, a VTB to generate a WLAN signal, and then I just apply that to the bandpass filter and the notch filter to get a test signal. So yeah, so there are different ways to do it. You can use noise, you can use a WLAN source. Okay. Then this, the amplifier under test is this. It's just a behavioral model in this case, but you can certainly use a different model. These simulations run a lot faster if you first generate the test signal rather than regenerating it every time. So I figured out that you want to run this simulation and generate an ideal WLAN test signal with a notch in it first, and then reuse this in subsequent simulations. So that's this result. Are there any questions about this so far? Yes?
I don't want, are you continuing to present?
Yeah, I'm going to continue to present.
Maybe after that.
Okay, all right. Well, this, you can add a load pool also to this. I have a, in this case, I'm running a load pool. I haven't talked about this today at all, but you can run load pool simulations with a modulated signal. It doesn't have to be a sinusoid, a CW signal. It can be modulated. So if you want to look at how the noise power ratio changes as a function of the load, you can do that, and you can plot EVM and ACPR and other things as well. But so in this case, I'm sweeping out a circular region. I have a simple power amplifier, but this is at the transistor level, and I want to see how the NPR changes, or for what loads give the best EVM and the best NPR, for example. In this case, I'm doing a power sweep. I'm not doing the optimization technique, but you can take the data and in post-processing interpolate it to see, say, the NPR contours at a specific alpha power or at a specific gain compression. These simulations take longer to run, but certainly a one-tone simulation, but they are possible to do. So this one is, okay, I don't have it because I removed it. so sorry, I removed the data set because it's large. Let me see if it's in here. No, not here either. Okay. It would take 10 minutes for me to run it, but yeah, you can get full data from it. It's not worth waiting for 10 minutes to see, but maybe I have it in the picture of it. No, I don't have a picture of it either. Sorry. Okay, sorry about that. But anyway, you can get contours of loadable data in PR data under loadable. The other method is using harmonic balance. And let me just show that. Okay, so this is, I made a video about this. So you can use harmonic balance to generate a multi-tone source like this, and then run a simulation, also using Monte Carlo to randomize the tones and integrate the across the notch to calculate the NPR. But that's the technique used here. So I'm running Monte Carlo, harmonic balance, and a power sweep to calculate the NPR. But each one of these is a combination of multiple tones, and then there's a notch in the middle as well. So yeah, so if you have a wide band, a relatively wide band signal, then I recommend using harmonic balance instead of envelope. Wide band relative to the carrier frequency. So you can calculate it. This is the broadband spectrum, and this is the narrowband notch spectrum. And this is a behavioral model, so it runs quickly. Possibly a real transistor model could be used, depending on how complex a signal you want. You could have something as simple as this, which is just a handful of test signals and a notch, but it's probably not quite suitable.
네, 지금 설명드린 거는 저희가 와이드 밴드위드를 가지는 모듈레이티드 시그널을 이용을 해서 AC LR이나 EVM 관련해서 이제 로드풀 컨투어를 그릴 때 시간이 오래 걸리니까요. 저희가 이 하모닉 밸런스를 이용해서 어떻게 하면 좀 더 물론 정확하지는 않지만 어프록시메이트하게 이제 결과를 확인을 하실 수 있도록 하는 메소돌로지를 설명을 드린 거라고 생각해 주시면 감사하겠습니다. 혹시 관련해서 질문이 있으실까요?
I have two questions. I know just the definition of NPR, but I'm not really an expert. But it seems NPR is related to the OIDD or IMD, isn't it?
I think it's related to intermodulation distortion, certainly.
Yeah.
Yes.
Because, so if the amplifier has a good OIDD, instead of the load base maybe different load pool, maybe not just peak power, maybe low OIDD, then it will give a good NPR ratio. Is it true?
Probably. I've never investigated the link, the correlation, but it seems likely.
Not sheet, there is no signal, only the signal applied from the like maybe ACPR, it seems.
Yeah.
Okay. Then also the other question is, why does it matter in satellite communication? You mentioned this NPR is important in satellite communication.
I think it's, I don't know for sure, but I think maybe NPR is, well, satellite communication tends to have pretty wide signals, multiple channel signals. And I think it's easy to null out one of the channels in measurement. It's easy to just say, okay, I'm going to turn off a channel and then just use, in a spectrum analyzer, measure what appears in that channel at the output, that's the distortion due to all the terms mixing into it. I think it's a tradition from measurement, but I think probably error vector magnitude is the more, maybe the more accurate way, or a better specification, but NPR is still around because of tradition, maybe. But I'm not an expert on it.
Thank you.
Cool.